Good morning. We have started our discussion on standard single stage saturation cycle. Okay, so in this basically we are talking about the vapor compression refrigeration cycle. In this, the working fluid is actually any substance which is operating in the two-phase regime. Okay, so working fluid is changing its phase from liquid to vapor in the evaporator and vapor to liquid in the condenser. Okay, and if you recall, in this cycle actually we have first started with the reverse Carnot cycle. Then to address the challenges, practical challenges associated with the reverse Carnot cycle, we have come to actually this cycle, okay, which is called as vapor compression cycle. And moreover, this cycle is identical to that of the reverse Carnot cycle. So in reverse Carnot cycle, particularly the involved, sorry, reverse Rankine cycle. In reverse Rankine cycle, the processes involved were 1 to 2 is isentropic compression, 2 to 3 was isobaric heat rejection in the condenser, then 3 to 4 is isentropic expansion in the turbine, and 4 to 1 was the isobaric or isothermal heat addition in the evaporator. Okay, so if this point 1 remains within the liquid vapor dome only up to the saturated vapor point, then I can call heat addition process as isothermal as well. However, in the cycle, the except for standard cycle, in standard cycle our aim is that we have to stop at this point only, but in practical cycles we can actually go beyond this point also. So beyond this point, whenever it will be moving on the constant pressure line, temperature will not remain constant. Okay. Another important issue, we discussed that if we use turbine in this cycle, then turbine is nothing but a steady flow device. For a steady flow device, work done is directly proportional to specific volume into pressure drop. Okay, and at point 3, whatever the substance we are expanding, it is in the liquid state, and typically liquid has a negligibly small specific volume in comparison to the vapor phase. That's why whatever the amount of work you will be getting in this isentropic expansion process from the turbine, that will be very small. And you know that whenever you have to practically install the system, it's not the difference of enthalpy which is the actual amount of work we get, but in addition to that, shaft will be rotating, it is put on some bearings, there can be some gear arrangement. So all these transmission things will also be leading to certain amount of losses. So if your amount of work is very small, then this work may not be sufficient enough even to overcome the losses, and ultimately you will be getting nothing but just kind of a zero output out of this turbine. Okay, so that is the reason. And another important issue is the cost of turbine is actually very high. So that can actually increase the overall cost of the system significantly without any added advantage of the turbine, which actually could be in terms of work if we expand high specific volume substance over it. Okay, so what we will be now doing, we'll try to go towards the more practical vapor compression system, in which from process 3 to 4 turbine is replaced by expansion device. Okay, and there are multiple practical expansion device available. For example, the oldest systems were having very small capillary, long capillary tube as expansion device. Then nowadays we are having some automatic this orifice size controlled expansion devices. Then there can be some porous structure as an expansion device. When the fluid will be flowing through the pores, ultimately it will be decreasing pressure. Okay, so the process which takes place in the expansion device, that process is actually throttling process. Okay, basically what is your aim? Your aim is to decrease the pressure from P3 to P4, or condenser pressure to evaporator pressure. Then only you will be able to come to this evaporator side. That is first point. And second point also, whenever you are decreasing the pressure, the temperature should also decrease from condenser temperature Tc to evaporator temperature Te. So these are the two things which we need to decrease. Okay. Now of course, it's very clear to us that if we have to decrease the pressure, we have to actually provide some restriction to the flow. Okay, so that restriction, what we can do, that if we have bigger tube, in front of bigger tube I can place very small diameter capillary tube. So whenever flow will be happening through that, then pressure drop across that capillary tube will be large. So it will be decreasing the pressure at its two ends. Okay. Similarly, if you take a valve and in the valve if you make very small orifice, then also what will be happening? You have created a significant restriction. Say you are having this type of pipeline, and in this pipeline now you have created significant restriction and you are allowing flow to happen only through this small portion. Again a restriction. So if you see in upstream and downstream, there will be decrease in pressure. So it means that whenever we are using this type of device, then always my pressure will keep on decreasing. And also, when the fluid is moving from point 1 to point 2, are you adding any heat or doing any heat exchange with the surroundings? No. So it means there we do not have any heat exchange. Do we have any work exchange? No. We do not have any device which is producing work or which is consuming work. Okay. So in this process, what will be happening? Pressure is decreasing, but if I apply steady flow energy equation, what will happen? Please tell me. Yes. So in expansion device, we will be having throttling process. So in a throttling process, say this is my pipe and here I am having some arrangement which is actually generating the obstruction over here to do the throttling process. Okay. So this is my point 3 and this is my point 4 dash. So I will be finding that if P3 is the pressure over here, P4 dash is pressure over here, P4 dash has to be less than P3 because this restriction will lead to decrease in pressure. Is this point clear? Now if I take a control volume across this. So if I take a control volume across this, is this control volume exchanging any heat with the surroundings? Zero. Sorry, equal to 0. And what about work? There is no work exchange, equal to 0. So if you apply steady flow energy equation, then heat interaction, that is 0, plus incoming enthalpy H3 equal to work interaction 0 plus outgoing enthalpy H4 dash. So it means H3 equal to H4 dash, neglecting the changes in kinetic and potential energies. Okay. So from here I can say that throttling process is isenthalpic process. Okay, so it means that now if I replace the turbine and if I plot the TS diagram for the cycle, okay, what I will be having? This will be my process 1 to 2. And then 2 to 3, and now from point 3 I cannot move in an isentropic fashion. So throttling process is nothing but an irreversible process. So the point is, if you create a restriction by having higher pressure on the left side, you can move from this pressure to this pressure. But can you move from low pressure to high pressure in the backward direction in this throttling process? No. So it means it's nothing but a irreversible process. At the same point of time, whenever you are creating this obstruction, fluid will be coming with high velocity and striking with this. It will lead to lot of eddy formation over here. So like we study in fluid mechanics. Okay. And these eddy formation etc. will lead to significant amount of losses. Okay. So it means it leads to entropy generation. So that's why the process, when I will be moving from 3 to 4, isenthalpic process will be something like this. And why I am representing it with dashed line? We all know that all the reversible processes, these are quasi-equilibrium processes. The meaning of quasi-equilibrium process is in between the initial and final points, I can represent all the intermediate states. That's why I can confirm that this will be the process path. But when I have irreversible process, I cannot know the intermediate states because process is not quasi-static. That's why we represent it with the dashed line. Okay. Now comes another point. One issue is addressed. that if we create restriction with the help of an expansion device, then what I can do, I can decrease the pressure. But what about temperature? If I create restriction, will there be always decrease in temperature with the pressure? Please tell me. Temperature will always decrease, or there can be some other possibility? Okay, both possibility. Anyone else? What could be the reason for increase in temperature? Why it will be increasing? In a throttling process, does temperature always decreases, or it can increase also, or it can remain constant? There are three options. Please tell me. Have you heard of any term called as Joule-Thomson coefficient? What is Joule-Thomson coefficient? Okay, can you tell me what is Joule-Thomson coefficient? Say you have a throttling device. Okay, this is a throttling device. You have some inlet state at point I and exit state at point E. Is this point clear? All are clear with this point? Now, let us consider if I draw temperature pressure diagram. So initially my state will be Pi and Ti. Is this point clear? So say I will be somewhere over here. Now I have regulated this valve at certain opening position. Okay, and corresponding to that opening position, say my exit state is PE1 and temperature is TE1. Is this point clear? Now what I do, if I further create restriction, then what will happen? My say valve was initially more open, I have further created the restriction and allow the fluid to flow again from the same inlet state. What will happen? Decrease in pressure will be more. Decrease in pressure will be more. So say I will be having some another point PE2 and TE2. So in this process you can see when I am starting from Pi, in this exit state pressure has decreased, temperature has increased. When I started from this point and reached to this point, then again pressure has decreased and temperature has increased. Then I'll be having, say, now I have created more restriction and again starting at the same point I. So what will happen? I'll be having more decrease in pressure. So now I am having more decrease in pressure as well as curve has also started shifting in the downward direction. It means temperature has also started decreasing. So this is PE3, T3. Likewise, if you keep on doing, you will be getting for every time corresponding to inlet condition, you can get multiple exit pressure and temperatures. Okay, if you join locus of all these points, you will get a line. Okay, and this process is nothing but a what type of process? Constant enthalpy process. So it means this line must be a constant enthalpy line. Is this point clear? So typically on during a throttling process on temperature pressure diagram, constant enthalpy lines looks something like this. Okay, say this is H1 enthalpy, H2 enthalpy, H3 or H4. Is this point clear? Now you can see I can define one coefficient mu Jt, which is called as Joule-Thomson coefficient, and it is generally given as the slope of temperature pressure plot for a constant enthalpy process. Okay, so that is called as Joule-Thomson coefficient. Now, in this region, if you see, this is some point where slope is changing. This is the point where slope is changing. On the right side of this point, what is my slope? If say I start from this initial condition and this is my exit condition, 1, 2, what will be slope? T2 minus T1 divided by P2 minus P1. T2 is greater than T1, so numerator will be, slope is T2 minus T1 by P2 minus P1. Now T2 minus T1 is positive and P2 minus P1 is negative. So it means on the right side of this I am having mu Jt as less than 0. Okay, and in the this side what I have, mu Jt is greater than 0. If I take any points, say 3 and 4 over here, okay, so mu Jt will be greater than 0 because both temperature and pressure are decreasing. So this point where slope becomes 0, this point is called inversion point. Okay, and if I go on the left side of this, then, and this entire locus of all the inversion points, it is called as inversion line. In the left side of this, I have slope of the Joule-Thomson coefficient as greater, or so value of Joule-Thomson coefficient as greater than 0. And at the inversion point, I will be having mu Jt equal to 0. Okay, so it means that if I operate my throttling device in the negative value of Joule-Thomson coefficient, then throttling will lead to increase in temperature. If I operate it in the negative, if I operate it in the positive value resign, then I will be having cooling because of the throttling process. And if I operate it near the inversion point, then there will be no change in temperature. Okay, and moreover, if you calculate, so mu Jt can also be calculated from thermodynamic property relations, and from thermodynamic property relations, if you calculate mu Jt for ideal gas, you will be finding mu Jt for ideal gas is always equal to 0. It means that if you do throttling of an ideal gas, there will not be, of course, there will be decrease in pressure, but there will not be any change in temperature of the ideal gas. That is the reason whenever we were talking about the gas refrigeration cycles, we have used turbine or compressor. We did isentropic expansion and expansion. We didn't do isenthalpic expansion. Okay, because if enthalpy is a function of temperature for the gas, so if enthalpy remains constant, then temperature will also remain constant for ideal gas. Okay, so Joule-Thomson coefficient for ideal gas is always equal to 0. And whenever we are operating with the refrigeration, in the refrigeration systems, always our aim is that when in process 3 to 4 days, we are decreasing the temperature, then ultimately what should happen? Always we are decreasing the pressure, along with decrease in pressure, temperature should also decrease. Okay, so in the throttling device, temperature should also decrease, then only our purpose of changing the temperature from condenser temperature to evaporator temperature in the throttling process will be solved. Otherwise, this purpose will not be solved. I cannot move in a cycle. Okay, is this point clear? So it means that whenever a throttling device is operated in the operated for a refrigeration cycle, it is always operated in the regime where Joule-Thomson coefficient is greater than 0. Okay, so this zone of the curve is known as cooling regime, and this zone of the curve is basically our heating regime. Okay, so always you have to operate your throttling device or expansion device in vapor compression refrigeration cycle, particularly in the positive regime of the Joule-Thomson coefficient. Is this one clear? Yes.
If you are taking two different pressures with a large difference between them, how can we say that the throttling device is going to follow that curve?
So the point is, whenever you start from this point to this point, means you are saying that if you move from this point to this point, then pressure ratio is small. Okay, but if pressure ratio is large, it means your one point is here, other point is here. Okay, so the point is, this is the reason, whenever along with this there are few more additional reason, but this is also one of the reason when we operate with very large pressure ratios in the refrigeration cycles, we don't operate in a single stage cycle, we operate in multi-stage cycles. Okay, so what are the limitations of single stage cycles and how we overcome these by using multi-stage cycles, that I will describe in the subsequent lectures. Is this one clear? So if you have to operate across the very large temperature limits, say minus 42 plus 60 degrees Celsius, of course you will be having very high pressure ratio, and for achieving that high pressure ratio, you are saying that it may so happen in this zone you may not be able to achieve the entire pressure drop. Okay, so if you are extending, so it is going beyond this region, then we will not be doing expansion in a single stage. We have to go for the multiple stages. Okay, so that we will subsequently discuss. Up to this point, anyone is having any issue? Now, you can see this is your new cycle after removing the turbine. Okay, all are clear with this point? So this is our standard single stage saturation vapor compression cycle, triple S cycle. Okay, is this one clear? Single stage means we are doing expansion and compression in a single stage, and saturation means at the exit of evaporator and at the inlet of compressor my state is saturated. Okay, and standard means because this is the first variant coming from after modifications in the reverse Carnot cycle, so that's why we are calling it as standard cycle. All are clear up to this point? Now in this cycle, what will be refrigeration effect? Specific refrigeration effect, that is refrigeration effect per unit mass flow rate, H1 minus H4 dash. Okay, and H2 minus H3 will be my expansion, this heat rejection, and H2 minus H1 will be the work. Okay, and it will be now the net work supplied to the system, because I do not have any work output. Okay, so now COP of system will be simply equal to H1 minus H4 dash divided by H2 minus H1. So earlier you were having with negative sign some term which is representing the work done by the system. So that term is now gone because we do not have any work produced in this particular cycle. Okay. Now after this, it is important always to compare the performance of a cycle with the reference cycle. So what is reference cycle? Reference cycle is nothing but our Carnot cycle. So now we'll try to compare triple cycle with Carnot, reverse Carnot cycle. So comparison of okay, so let me first draw the triple S cycle. Is this point clear? And if on the same cycle I have to superimpose the Carnot cycle, how it will be looking like? Let me use keyword 4 for this, and state point 4 for this, and 4 dash for this. Okay, all are clear with this point? Or let's be consistent with the previous one. Okay, so it is 4 and this one is 4 dash. This will be my point 2 dash, and then I should move in this fashion for Carnot cycle in an isothermal fashion 2 dash to A. All are clear with this point? Anyone is having any doubt? Now one important point is, this is nothing but a cyclic process. If I compare reverse Carnot, then also we have a cycle. If I compare this standard vapor compression cycle, then also I have nothing but a cycle. For a cyclic process, always cyclic integral of del Q is equal to cyclic integral of del W. This point we know from first law of thermodynamics. Another important thing we know that for a reversible process, heat is equal to area under the temperature entropy diagram. It is integral of TDS. Okay. So now, if I say that what is my amount of heat rejection in the condenser? Amount of heat rejection in the condenser always will be equal to area under 2A3 line. Okay. Whatever will the area below this line, that will be nothing but my heat rejected in the condenser. Is this one here? And if I talk about heat added to the refrigerant in the evaporator, then heat added QE for reverse Carnot, it will be simply equal to area under 4 to 1 line, and for triplet cycle it will be area under 4 dash to 1. Is this point clear? Now process 1 to 2 and 3 to 4 or 3 to 4 dash, in these processes we do not have any heat interaction. Okay, so it means that cyclic integral of delta Q, many times I have written, it is nothing, or small delta Q, let me write because I am writing on per unit mass basis. So that will be QC minus, QC minus QE. Okay, and or minus QC plus QE, because QE is the heat added to the substance and QC is, so it will be negative value. And this must be equal to the net work done, W net, and work done, net work done is negative, it means work is done on the system. So now it means that if I take difference of these areas, that will be giving me the work done required by the system, okay, or the cycle. So what will be work done for reverse Carnot cycle? Please tell me. For reverse Carnot cycle, 2 dash A3, this will be the rejected heat, and the heat added will be from 4 to 1. So this minus this, what will be? Area enclosed by point 1, 2 dash A341. This area will be actually work required by the system. All are clear with this point? And if you have to calculate the area for other cycle, then starting from 2A3, this will be, there will be 2 additions. What are the 2 additions? One will be this addition and other will be this addition. All are agreeing to this point or not? Please tell me. Still not clear? Clear? Otherwise, I have to then draw it with again extending. Shall I extend or is it fine? It's fine. Okay. So you see, area was this much was the area for the reverse Carnot cycle in this entire periphery. Okay. And for triple S cycle, because heat rejection is area under this entire thing minus area under 4 to 1 dash. That is the total work done. So when you decrease, remove this area, then along with the Carnot cycle, one additional area is coming from here and one additional area is coming from here. Okay. So say this area is A1 and this particular area is called as superheating horn. This is called as superheating horn. And this area, let me call it to be A3, and this area is called as actually throttling loss. Is this point clear? So this is the additional work which will be required now in addition to the reverse Carnot cycle. So one is because of the throttling process, so that is throttling loss, and other is because of the superheating of the cycle. We cannot move in an isothermal fashion, so that is actually called as superheating horn. All are clear up to this point? Now let me discuss one key aspect. If I represent temperature entropy diagram, so my constant pressure lines are something like this. This is PC, and in subcooled region it extends something like this. Then this is PE. Here also it will be extending something like this. So generally what happens, the slope of constant pressure line in the subcooled region is very close to the slope of the saturated liquid vapor curve. All are you agreeing to this point? Okay, so generally the nature of the saturated liquid line is such that whatever the constant pressure line on TS diagram I will be having in the subcooled regime, that will be having actually slope very close to that of the saturated line. So what we do generally, even when you have learnt using the steam tables, at that time in your thermodynamics course it would have been taught that we can make one assumption that this constant pressure line in the saturated vapor regime is just following the saturated liquid vapor dome. All are clear with this point? Now if we make this assumption and if I now go with the same cycle, so this was point 2, this was point A, this was point 3. What was the area under this? This entire was the area under this. Okay, and it was nothing but QC. QC is H2 minus H3. Now if I take a point 0 over here, okay, and let me also do one thing. If I take the entire area from 2A30, it will be representing nothing but H2 minus H0. Okay, what will be H2 minus H0? Entire area. It will be including this area as well. All are clear with this point? And what will be the area below 0 to 1? That will be nothing but H1 minus H0. Is this point clear? So area from 0 to 1 will be H1 minus H0. Now what is our compressor work? H2 minus H1. Compressor work is H2 minus H1. And compressor work is the only work now we have in the network. So can I write compressor work as H2 minus H0 minus of H1 minus H0? Can I write it? Okay. Simply I have just added H0 and subtracted H0. Okay. So what is H2 minus H0? H2 minus H0 is this entire area. And what is H1 minus H0? This area. Okay. So whatever area is now remaining area is this much. That is the remaining area. All are you agreeing to this point? It means this remaining area, whatever I have shown with the green hatching, this remaining area is nothing but my compressor work WC. Up to this point all are clear. Now you compare the previous figure. In the previous figure you are having one superheating horn. That superheating horn is remaining as it is over here also, participating in area. But in the previous figure you were having one additional area from 4 to 4 dash, which I was calling as throttling loss. But when I made this approximation, this throttling loss is gone from here and it has gone to this additional area from 0, 4, 3. All are clear with this point? So I can say that if I call this particular area, which is from 0 to 4 to 3, if I call this particular area as nothing but my A2, then by comparing this figure and the previous figure, I can say that if this area is A2, then I can say A2 is equal to A3. All are clear with this point or not? Is it clear? A2 is equal to A3. If A2 is equal to A3, then the work done required by the triple S cycle is nothing but work done required by reverse Carnot cycle plus A1 plus A3, and A3 is identical to A2. Clear? And what is A2? A2 you have to understand very clearly, it is nothing but this area. If from 3 point I draw isentropic line, that isentropic line with saturated liquid line, whatever area it will be encapsulating, that is my A2. And for comparing this figure and this figure, we can say that A2 equal to A3. So that's why I can say my throttling loss will be depending upon the slope of the saturated liquid line. Okay, because if this slope is more vertical, then throttling loss will become, if this slope becomes purely vertical, so then throttling loss will become 0, because 3 to 4 will directly coincide with this one. How it will coincide, that I will explain further. But for the time being, we are considering that A2 equal to A3, and that's why work done in the triple S cycle is equal to work done of reverse Carnot plus A1 plus A2. Now, other important parameter is refrigeration effect. What was the refrigeration effect in actual cycle? In Carnot cycle, refrigeration effect in Carnot cycle is reverse Carnot is equal to how much? H1 minus H4, and refrigeration effect in triple S cycle is H1 minus H4 dash. So it means that in triple S cycle, I can say refrigeration effect of reverse Carnot minus A3, throttling loss, and A3 I have already written as equal to A2. So I can replace it with A2. So it means that my refrigeration effect of triple S cycle will be nothing but refrigeration effect of reverse Carnot minus A2. Okay. Now if you calculate the efficiency of the cycle, second law efficiency of the cycle, okay, what is second law efficiency? COP of actual cycle divided by COP of Carnot cycle. So it means that second law efficiency of our actual cycle will be COP of triple S divided by COP of reverse Carnot. What is COP of triple S? RE RC minus A2 divided by WRC plus A1 plus A2 divided by COP of reverse Carnot. Now you take these two common. If you take these two common, then RE of RC divided by W of RC will be coming common in the numerator, and what you will be getting? 1 minus A2 divided by RE of RC divided by COP of RC into 1 plus A1 plus A2 divided by WRC. This will be cancelling out. So ultimately you can calculate that your efficiency is nothing but 1 minus A2 divided by refrigeration effect of reverse Carnot divided by 1 plus A1 plus A2 by W of RC. What it means? It simply means if you can decrease A1 and A2, if you can decrease A1 and A2, what will happen? Efficiency will increase. It means your actual cycle will become more closer to the Carnot cycle. Agree to this point? So from this we can clearly see that in the numerator A2 is a negative effect. It's a penalty because it is decreasing the overall value of the numerator. So if A2 is small, value of numerator will increase, and moreover in the denominator A1 and A2 both are positive terms which are just increasing the denominator. So it means that if I can decrease the value of A1 and A2, I can increase the efficiency of the reverse Carnot cycle, which will make it more closer to the I can increase the efficiency of triple S cycle, which will make it more closer to the reverse Carnot cycle. All are clear with this point? So it means now our attempt should be to increase the value of to decrease the value of A1 and A2. And to decrease these values, what we can do? We can choose different type of working fluid, because there are different type of working fluids which have their own characteristics. Now let me come to different type of TS diagrams. Say I have a working fluid whose saturated liquid line is almost vertical. In this case, how I will be having cycle? This is point 1. Okay, this will be point 4. So 3 to 4 and 0 to 4 are actually 0 to 3 are coinciding. So it means for this type of cycle A2 for this type of working fluid A2 is 0. However, it has significant amount of A1. A1 is large. Okay, so one type of working fluid could be whose slope is almost vertical for the saturated liquid line. This type of fluid will be having almost negligible throttling loss, whereas it can have large value of superheating. Other type of substance could be, second category of substance could be, see, Whenever we talk about working fluid, we talk about in refrigeration ammonia as a refrigerant. We talk about R134A. We talk about CFCs. So there are large number of fluids available. So depending upon their, even water is also used as a refrigerating medium. So depending upon the nature of their substances, the shape of liquid vapor dome is different for different substances. So what could be the different possibilities of the shapes that I am discussing over here? Then which refrigerants comes under the category of shape, that we will discuss later, or even that you can read from textbook as well. Okay. So second category could be where a refrigerant with positive slope of saturated vapor line. You can see over here entropy is also increasing, temperature is also increasing. So for this saturated vapor line, del T by del S is greater than 0. It means saturated vapor line has what type of slope? Positive slope. So if you go for this, now if you do the isentropic compression, what will happen? Your superheating horn A1 is approaching to 0, but A2 is large. Okay, superheating horn A1 is becoming 0, but A2 is large. So this A1 will become 0 for a substance whose slope is actually, slope of the saturated vapor line is positive. Okay, all are clear with this point? And then of course we do have situation, I don't want to go even this regime in this regime, I want to go to regime where both A1 and A2 should be small. Okay, or of course my aim should be that both should be 0, but ultimately if say one I am making equal to 0 and other I am just completely avoiding, that is also not possible. And again this is creating more challenge also. If I go with this positive slope, then in this particular region I am operating with the two-phase regime. Okay, so again two-phase regime in the compressor is actually a challenging to deal with. Okay, so this is one, this is two, and what about third? What could be the third possibility? Third we have already done. So we have a TS diagram where we typically have asymmetric saturated liquid and vapor lines, and in this asymmetric liquid and vapor lines we can adjust our pressure ratios so that we can adjust our, we can use the working fluid in such a way for a particular arrangement such that this area and this area are smaller. So always for the entire range, for wide spectrum of the range of operation, you cannot ensure this, but what we can do for limited range of applications, where say our operating range is not changing much, there we can use the working fluid which is actually meeting these requirements. Is this one clear? So it means that the shape of the liquid vapor dome has significant control on the performance of the what? Triple S cycle. Have you agreed to this point? So it means the shape of the liquid vapor dome can significantly control the COP of the triplet cycle and its deviation from the reverse Carnot cycle. This point we have established over here. So it means the properties of the working fluid will be very important in controlling the performance of the overall system. Now, another important aspect is, whenever we have done this thermodynamic analysis of the vapor compression cycle, what we found? We found that heat rejection, work input, etc., all are written simply in terms of difference of enthalpy between the two state points across each steady flow device. Okay, so it means that if I plot my diagram in such a way so that by just comparing the difference of enthalpy, I can actually determine the performance of the system. Okay, so that is the reason whenever we do work with the refrigeration cycle, majorly we plot pH diagram, pressure and enthalpy diagram. Because if I plot the pressure and enthalpy diagram, then you can see my enthalpy will be on x-axis. By just measuring the length of the different processes, I can actually on x-axis, projected length on x-axis, I can actually calculate refrigerating effect, work input, heat rejected, etc. And analysis of the system becomes easier. Okay. So on a pressure enthalpy diagram, typical liquid vapor dome appears something like this, maybe not very correct. So this is how liquid vapor dome appears on a pressure enthalpy diagram. And on this diagram, because I have to also represent the isentropic processes, so for isentropic process, the constant entropy lines in the superheated regimes move something like this. So as long as these keep move away from the saturated vapor line, these actually diverges. Okay. So on this, if I have to plot my standard cycle, how it will be? Please tell me. This is point 1. From point 1 to 2, I have to follow a isentropic line because my process will be isentropic compression. So this is constant entropy line, and this is 1 to 2. Then 2 to 3 I will be having constant pressure, heat rejection, and then 3 to 4 what? Isentropic or isenthalpic? Because triple S cycle we are talking about, so isenthalpic. So it will be a vertical line, and vertical with dashed line. Say this is my point 4 dash and this is 1. Now what you can do if you have to calculate refrigeration effect on the pH diagram, you will be simply calculating this length, and this length h1 minus h4 dash will become your specific refrigeration effect per unit mass. If you have to calculate work done, simply calculate this length. This length will be h2 minus h1 and will become equal to compression. If you calculate this length, simply this length if you calculate, that must be h2 minus h3. Okay, and it will be equal to heat rejected in the condenser. Okay, so it means that if you work with pH diagram, then your analysis of the cycle becomes quite easy. Is this one clear? Because simply projection of the line length on the x-axis will give you all your important required parameters. Okay. Along with this, my refrigeration effect is m dot into h1 minus h4 dash. Specific refrigeration effect is what? h1 minus h4 dash. There is one more term which is called as volumetric refrigeration effect. What is the meaning of volumetric refrigeration effect? Mass flow rate you can write as nothing but the, at point 1, mass flow rate you can write density of point 1 into volume flow rate at point 1 into h1 minus h4 dash divided by volume flow rate v1 dot. Okay, so per unit volume flow rate, whatever effect will be there, that will be nothing but rho 1 into h1 minus h4 dash, and it will be equal to h1 minus h4 dash divided by rho 1 you can write 1 by new 1, where this new 1 is nothing but the specific volume at point 1. Why this is important? Can you tell me why volumetric refrigeration effect is important? Ultimately, you have to design the size of evaporator, size of compressor. So how much volume flow rate the compressor should be able to handle, that will be depending upon the volumetric refrigeration effect. So at point 1, whatever is the specific volume or density of the working fluid, that will be controlling for a given or required mass flow rate, what should be the volume flow rate that compressor should be able to handle. Okay, because if you use a reciprocating type compressor, then when you are moving the compressor from bottom dead center to top dead center, in that process it will be pushing a fixed amount of volume, which is called as displacement volume or swept volume. Now if your density is low and you have to pass more mass flow rate, then you have to take the large size of that reciprocating piston cylinder arrangement. Okay, and if you have to pass, if your density is high, so then for same mass flow rate, the size of the compressor piston cylinder arrangement will be less. Okay, so that's why volumetric refrigeration effect is very important, because ultimately it helps in deciding the size of the compressor which we will be using. Okay. Okay, we'll stop with this and we'll discuss further in the next class.